So, welcome to this lecture number 35 of our course on fundamentals of transport processes 2, where we were looking in the last lecture at boundary layer theory. Boundary layer theory is used for the flow very close to surfaces when the Reynolds number is high. If the Reynolds number is high and you just simplistically neglect the viscous terms in the momentum conservation equation, then you get the potential flow equations if the flow is irrotational as well. For that potential flow solutions, we found that you cannot satisfy the tangential velocity boundary condition at the surface. You can satisfy the normal velocity boundary condition at the surface, but one cannot satisfy the tangential velocity boundary condition at the surface. So, there is a correction to the outer potential flow very close to surfaces, where you have to take into account the effect of the viscous stresses in a thin layer close to the surface. In the limit of high Reynolds number, the thickness of this layer becomes smaller and smaller, so that the gradients in this layer become larger and larger in such a way that there is a balance between the inertial and the viscous terms in the conservation equation, even as the thickness of this layer goes to 0 and the Reynolds number goes to infinity. So, it is easiest to illustrate by the flow past a flat plate of length L, where we take x as the streamwise direction and y as the cross stream direction, the what is called the cross stream direction perpendicular to the direction of the mean flow. There is a velocity u. Okay. This velocity, as I explained, could in general be a function of x. Okay. And there is a thin boundary layer near the surface. If you are outside this boundary layer, then viscous effects are small because the Reynolds number is large. However, when the thickness of this region becomes smaller and smaller, okay, you have the velocity that is increasing to the outer flow velocity within a smaller and smaller region. So, as the thickness of this region becomes smaller, the gradients become larger. There is the cross stream derivatives of the velocity with respect to the y coordinate become larger. The viscous terms are proportional to the second derivative with respect to the y coordinate. So, if the length scale is sufficiently small, the derivative is sufficiently large in such a way that you can get a balance between the inertial and the viscous terms. And if you recall, we calculated what the boundary layer thickness should be. Delta, as you recall, is equal to nu x by u power half. Okay. So, this is basically delta by the cross stream thickness goes as the Reynolds number based upon x to the minus half. So, if the thickness goes as r e power minus half, then the viscous terms are proportional to the second derivative. They are r e inverse larger than what you would simplistically expect if you just scaled the boundary layer thickness, the normal, the cross stream coordinate by the distance x. And because of that, the inertial and the viscous term become of equal magnitude. So, as I said, you have an outer potential flow where you know what the velocity is. That potential flow, the relevant length scale for that potential flow is the macro scale. The pipe diameter, the thickness of the radius of the sphere in the case of immersed objects. In this particular case, it is the length of the flat plate L. Over length scales comparable to L, inertia is dominant and the viscous effects are neglected. However, as for a thin region near the surface, viscous and inertial effects become of equal magnitude. Okay. So, for the outer region, you have y goes as L, which means that y star is defined as y by L, that is the relevant length scale. Within the boundary layer, you have the y goes as delta, which means that eta, which is equal to y by delta. The two of these solutions have to match in an intermediate region where y is large compared to delta, but small compared to L. That can always be realized because delta is r e power minus half smaller than L. Therefore, one can always find an intermediate region where y is small compared to L, y is large compared to delta, the two solutions, the potential flow solution in the limit as y by L goes to 0 has to match with the boundary layer solution in the limit as eta or y by delta goes to infinity. For the outer potential flow in the limit as y by L goes to 0, the normal velocity has to go to 0, because the potential flow solution satisfies the 0 normal velocity boundary condition. Therefore, the normal velocity has to go to 0. The tangential velocity, u x is equal to some function of x, which we had called u of x, for y star going to 0. As y star goes to 0, as you approach the surface from above, the velocity u x is equal to some function of x, and u y has to be equal to 0. From the Bernoulli equation, we found that pressure has got to be equal to P naught minus half rho u square, so because u x is going to u of x, which is non-zero, because the potential flow is predicting a non-zero tangential velocity. U y is going to 0. So, for this particular case, we obtained simplified equations when the cross stream coordinate, when the length scale for the cross stream direction is small compared to the length scale in the streamwise direction. And these equations were the usual mass conservation equation, the momentum conservation was this, that was the momentum conservation equation in the x direction, and the momentum conservation equation in the y direction just reduced to partial p by partial y equal to 0. Now, the pressure for the outer flow, for the potential flow, for y star going to 0, the pressure is equal to minus half rho u x square plus u y square. Of course, in the limit as y star goes to 0, u x is equal to capital U and u y is equal to 0. So, the pressure just approaches P naught minus half rho u square. Therefore, dP by dx minus rho u du by dx. Since the pressure gradient in the y direction is equal to 0, the pressure in the boundary layer is independent of y. It is independent of the scaled coordinate in the y direction. Therefore, the pressure in the boundary layer is the same everywhere as the pressure in the potential flow, outer potential flow in the limit as y goes to 0. So, substituting this, we got the x momentum conservation equation as u x partial u x by partial x is equal to capital U du by dx. Note that this capital U is now only a function of x, it is the y tending to 0 limit of the mean velocity in the potential flow, plus So, these are the boundary layer equations, which we had solved for different cases, for the flow past a flat plate and for the stagnation point flow. In the last lecture, we were asking the question, what is the form of the mean velocity and the boundary layer thickness which will admit a similarity solution for the boundary layer equations. If you recall, the argument for a similarity solution was as follows. If I have a mean velocity profile, and if I have a boundary layer solution at a given location x within the flow, the solution for the velocity profile should not depend upon the total length L, because the downstream edge of the plate is downstream of this location x. Therefore, the velocity profile should depend only upon x itself as well as the mean flow velocity capital U and the kinematic viscosity nu. Okay. And on that basis, we have obtained the boundary layer thickness, which was at a specific location x measured from the upstream edge as this one. Okay. So, we had got the solution for delta just based upon dimension analysis, where u is in general a function of x. In the last lecture, we had stepped back and asked the question, what are the specific forms of delta and u which will actually admit a boundary layer solution. Okay. So, we had chosen for our as a starting point a postulate that we can write the stream function flow for the flow as u delta times f of eta, where eta is equal to y by delta of x. Okay, eta is equal to y by delta of x, and the stream function is u delta times f of eta. Note that the stream function, the velocities are related to the derivatives of the stream function. So, the stream function has to have dimensions of velocity times distance, which this one does have if f is dimensionless. Okay. Both u and delta in this case are functions of x itself. Okay. So, we chose this form, u is a function of x, delta is a function of x, and we use this in order to substitute this into the mass and momentum conservation equations. When we express the velocity in terms of the stream function, u x is equal to partial psi by partial y and u y is equal to minus partial psi by partial x, the mass conservation equation is identically satisfied. The momentum conservation equation is given by u x partial u x by partial x If you recall, in the last lecture, we had substituted u x, u y and its derivatives in terms of u and delta, and then simplified to get a differential equation for the function f itself. Okay. As you can see, u x, right, if I write eta is equal to y by delta of x, this u x is just equal to u times df by d eta, okay, where eta is a similarity variable. So, u x is just equal to u times df by d eta, and I have a second derivative of u x with respect to y here. So, I will get a third derivative here with respect to of f with respect to eta. Okay. So, we substituted those equations into the momentum conservation equation, calculated u x, u y and its derivatives in terms of f, and substituted it in here in order to get an equation, a similarity equation for the function f of eta. The equation that we had got was d cubed f by d eta cubed plus into 1 minus df by d eta the whole square plus of u delta into f d square f by d eta square. This has to be equal to 0. So, that was the equation, the equation that we got for f after substituting for the velocity u x, u y in terms of f into the momentum conservation equation, as also for substituting for this particular velocity. And if you recall, we divided throughout by the prefactor of the highest derivative in order to get a dimensionless equation. Obviously, this equation admits a similarity solution only if these two functions are both simultaneously equal to constants. Okay. If they are not equal to constants, if they do depend upon x, then the final equation that I get is not an equation of f in terms of eta alone. It is only if these two are constants do I get a final equation in which can be solved for getting f in terms of eta, and thereby getting the stream function of the velocities. So, therefore, in the last lecture we had said that delta square by nu du by dx is equal to some constant beta, and delta by nu d by dx of u delta is equal to some constant alpha. So, this was the final solution that we got. Both of these functions, delta is a function of x, capital U is a function of x. However, both of these functions given here have to be constants, okay. And we were looking for solutions that satisfy this. Okay. So, rather than writing in terms of alpha and beta alone, okay, we had shown you in the last lecture that 1 by nu d by dx of delta square u is equal to 2 alpha minus beta. Okay. Rather than using these two, okay, my original equation I had to solve for these two. Okay. This third equation that I have is a combination of these two. Okay. So, it is a linear combination of the first two equations there. Okay. I have equation, this first equation 1, the equation 2. This third equation is a linear combination of equations 1 and 2. So, rather than solve 1 and 2, I can as well solve 1 and 3, because 3 is a linear combination of 1 and 2. Okay. So, therefore, I will solve these two equations in order to get the velocity profiles for which a similarity solution can be obtained. First things first, this equation number 3 basically gives you a relationship between delta and u. This equation basically states that 1 over nu d by dx of delta square u has to be equal to a constant, which means that delta square u is equal to 2 alpha minus beta times x plus c, just by integrating once. And as I told you, this constant c can always be set equal to 0 from the requirement that the boundary layer thickness has to go to 0 at x is equal to 0, which means that the location of x is equal to 0 corresponds to the upstream edge of the boundary layer. With that requirement, I can always set c equal to 0 without loss of generality. Okay. And this basically gives me u is equal to, I am sorry, delta is equal to I have a factor of nu here. Note that there is a factor of nu here, which basically comes out of this kinematic viscosity. Okay. So, therefore, delta is equal to So, this equation basically gives me delta in terms of u and x. Note that u is also a function of x. Of course, it does not have any additional information compared to what we already had. Just based upon dimensional analysis, we had written down that delta of x has got to be equal to nu x by u power half. We had already said that delta of x has to be equal to nu x by u power half. Of course, delta is just a boundary layer thickness. It is something that is used to define a dimensionless variable. Okay. I can always change delta by a constant factor. The solution expressed in terms of the scaled variable eta will change, but the solution expressed in terms of the original variables will be unchanged. So, I can always define delta with respect to an unknown constant. If you recall, in Fundamentals of Transport Processes 1, we had actually done the calculation by putting in an undetermined constant into the expression for the boundary layer thickness, then showing that it does not matter in the end. Okay. So, therefore, I can without loss of generality set 2 alpha minus beta equal to 1. Okay. U is positive in this particular case, because the flow is in the x direction. We can always align our x axis with the flow, and therefore, 2 alpha minus beta can always be set equal to 1 without loss of generality, because delta is known only to within a multiplicative constant. scaling that we are using for the y coordinate. So, this basically gives me back the familiar result nu x by u power half. It gives me a relation between delta and capital U. Okay. I have one more relation, which is of course equation 1, which I need to solve to find out what is the form of x that emerges. Okay. So, the second equation is delta square by nu du by dx is equal to beta. Okay. Substituting my expression for delta, okay. Delta square is nu x by u, okay. Delta square is nu x by u, and I have 1 over nu du by dx is equal to beta. This tells me that 1 over u du by dx is equal to beta by x. Therefore, log u is equal to beta log x, or the solution for this is u is equal to beta times x. I am sorry, k times x power beta. Okay. So, that is the solution for the velocity field. Okay. The velocity u of x has to be a power law in x in order to be able to obtain a similarity solution for this particular case. Okay. What are those solutions, the power law solutions? Okay. Recall that u of x is equal to limit, okay, for the outer potential flow, limit as y star goes to 0 of u x of x. It is the limit of the outer flow potential velocity in the limit as y going to 0 is capital U of x, and that has a power law dependence upon x. What are those velocity profiles which satisfy this condition? We have already seen them when we solved the potential flow equations. If you recall, okay, when we did potential flow, okay, the flow within a corner, okay, the flow within a corner, okay, of angle pi by m, okay, the flow within a corner of angle pi by m has a complex potential f, okay, is equal to a times x power m, has a complex potential f is equal to a times x power m, and the complex velocity is equal to m a times x power m minus 1. Okay. I am sorry, I should write this in terms of the complex variable z, m a z power m minus 1. Okay, that is a complex velocity. This is equal to u x minus I u y. Is equal to u x minus I u y. Okay. So, a z for a complex potential basically corresponded to a constant flow. Okay. For m is equal to 1, if you recall, we just had a constant velocity profile. For m is equal to 2, we had a stagnation point flow. Okay. This for m is greater than 2, you have flow in a corner that looks like this, m greater than 2. Okay. You can always also have m less than 1, the minimum value of m is a half, and m is equal to a half correspond to a flow that went like this. Okay. We had already seen this in our potential flow solutions. Okay. So, the complex velocity is m a z power m minus 1, which is x minus I y. I am sorry, it is equal to u x minus I u y. We would also express it as u r minus I u theta times e power minus I theta. So, what is the velocity capital U for this case? Okay, the velocity capital U is equal to the limit as y goes to 0 of u x. Okay. My complex potential is given by m a times z power m minus 1. Okay. I can also write this as m a times x plus I y power m minus 1, okay, because that is just x plus I y. Okay. In the limit as y goes to 0, okay, in the limit as y goes to 0, this just is equal to m a times x power m minus 1. Okay. In the limit as y goes to 0, okay, as y goes to 0. Okay. So, this is capital U of x, this is capital U of x. As you can see, it is a power law, okay, m a times m x y power m minus 1. Okay. So, this corresponds to this velocity provided k is equal to m times a and beta is equal to m minus 1, okay, beta is equal to m minus 1. So, these are the flows, the flow in a corner for which the velocity u x in the limit as y goes to 0 has a power law dependence upon the x coordinate. For these particular velocity fields, we can get a similarity solution. Okay. And for that similarity solution, the equation that has to be solved, as you recall, is d cubed f by d eta cubed, okay, plus delta squared by nu du by dx into 1 minus df by d eta the whole square plus delta by nu d by dx of u delta into f d square f by d eta square is equal to 0. Okay. As you know, we have already solved for delta square by nu du by dx is equal to this constant beta, which is equal to m minus 1, okay, for the corner flow. If we correlate the exponent beta to the exponent m for the complex potential in the flow through a corner, then beta is equal to m minus 1. And you can easily verify that delta by nu d by dx of u delta, okay, delta by nu d by dx of u delta will turn out to be half, okay, because okay, so I step back a little bit. Okay. Okay. So, this is equal to beta. We also know that we have set 2 alpha minus beta is equal to 1, okay, because that entered into the definition of the boundary layer thickness. Okay. This gave us that delta of x is equal to nu x by u power half. Okay. So, if you use this 2 alpha minus beta is equal to 1 and this is equal to beta, you can easily show that this is equal to half of 1 plus beta, okay, which is equal to m by 2. Okay. So, with these constants, the equation for the boundary layer can be written as d cubed f by d eta cubed plus beta 1 minus df by d eta square plus half into 1 plus beta into f d square f by d eta square is equal to 0. So, for different values of m, beta is equal to m minus 1 and you substitute the value of beta in here, okay, and you will get a solution for the boundary layer equations. If you recall, for the flow past a flat plate, okay, for the flow past a flat plate, you had a constant velocity, therefore, beta was equal to, I am sorry, m was equal to 1 and beta, which was m minus 1, was equal to 0. Okay. And for that particular case, the equation for flat plate, beta is equal to 0 and m is equal to 1. Okay. And we got f triple prime plus half f double prime is equal to 0. Okay, but beta is equal to 0 and m is equal to 1. For the stagnation point, the velocity was increasing linearly with x. So, that means that beta is equal to 1 or m is equal to 2. Recall that flow in a corner, the complex potential was equal to a times z square. Okay. So, beta is equal to 1 or m is equal to 2 and the equation we got was f triple prime plus 1 minus f prime square plus f double prime is equal to 0. is beta is equal to 1 or m is equal to 2. Okay. So, these are special cases of this more general velocity profile, okay, which for which one can get similarity solutions. Of course, for each particular case this equation has to be solved numerically in order to find out what the solution for the velocity profile is. Okay. So, for each particular case, for each corner angle, beta is equal to m minus 1, okay, where m is the exponent in the complex potential, and for that particular velocity profile this equation has to be solved numerically to get the solutions. We will not go through the numerical solutions here, but rather we will just look at the qualitative features of the flow. Okay. Recall that delta was equal to nu x by u power half. Okay. For these solutions, I should point out here that these are called this is called the Faulkner-Skan equation. The Faulkner-Skan boundary layer equation for velocity profiles in which capital U increases as an exponential as some power of x. Okay. So, these are the Faulkner-Skan equations for which one can get boundary layer solutions. For these solutions, delta is equal to nu x by u power half, which is equal to nu x by k x power beta power half. Okay. So, this is equal to nu by k power half into x power 1 minus beta by 2. Okay. So, if you recall, for a flat plate flow, for the flow past a flat plate, m is equal to 1 and beta is equal to 0. Okay. Because the velocity was not increasing, the exponential was 0 because the velocity was invariant with the x coordinate. For the stagnation point flow, we found that m is equal to 2, beta is equal to 1. Okay. Then you have corner flows with acute angles for which m is greater than 2, and then you have obtuse angles. Let us just plot these. Okay, for which okay. And then you can also have the flow that goes something like this. Okay. And then you can have a flow that goes something like this. Okay. M less than 1, and then you have this limiting case. M is equal to a half. So, those are the different kinds of flow profiles that you can have in a corner. Okay. So, we only looked at these two, the flat plate as well as the stagnation point flow as special cases. So, the more general flow profile, the boundary layer thickness goes as x power 1 minus beta by 2. That means, when beta is equal to 1, the boundary layer thickness is a constant. That is what we got for a stagnation point flow. For beta is equal to 1 or m is equal to 2, the boundary layer thickness is just a constant. Okay. For beta is equal to 0 or m is equal to 1, you have a boundary layer which is increasing as you go downstream. The thickness goes as x power plus half. Okay. Now, in between these two, you will find that the boundary layer thickness goes as 1 minus beta by 2. So, this m is equal to 2 means that beta is greater than 1 here. So, in this case, where beta is greater than 1, where m is equal in this case, when beta is greater than 1, when beta is greater than 1, okay, you are having a boundary layer which is decreasing with downstream distance. Okay. So, in this case you have BL thickness decreasing. Okay. In this case BL thickness is a constant. Okay. And when m becomes beta becomes less than 0 or m becomes less than 1, you have a boundary layer thickness which is increasing with downstream decreasing is increasing with downstream distance. Okay. So, the boundary layer thickness depends upon this parameter beta here. Okay. The boundary layer thickness depends upon the value of beta that you have. Okay. Of course, if the boundary layer thickness increases or decreases, then of course the shear stress goes as 1 over the boundary layer thickness. Okay. The shear stress tau x y is equal to mu du x by dy, okay, which is equal to mu u by delta square d square f by d eta square. Okay. So, that is the boundary layer thickness. This goes as mu u by nu delta goes as nu x by u, delta square goes as nu x by u times d square f by d eta square. Okay. You recall that ux was equal to u times df by d eta, which means that partial ux by partial y is equal to u by delta d square f by d eta square. Okay. So, I should have delta here as a half. Okay. So, is equal to mu u power 3 by 2 by x power half nu power half f double prime. Okay. So, this is the expression for the shear stress. Capital U goes as k times x power beta, and I have x power half in the denominator. Okay. So, this becomes mu k power 3 by 2 x power 3 beta by 2 minus 1 by 2, okay, by nu power half f double prime. That means that the shear stress goes downstream as x power beta minus 1 by 2. Okay. So, therefore, the shear stress increases downstream for 3 beta greater than 1 or beta greater than 1/3, whereas it decreases downstream for beta less than 1/3. Okay. Okay. So, m is between 1 and 2, that means that beta is between 0 and 1, okay, and m less than 1, beta is less than 0, and m is equal to a half means that beta is equal to minus 1 by 2. Okay. So, beta, which is m minus 1, goes all the way from minus a half all the way to large values. As the value becomes larger and larger, you get the flow in a corner of a smaller and smaller angle, because the angle is equal to pi by m, which will be pi by beta plus 1. Okay. And depending upon the angle, you get either a flow that is accelerating downstream, because x power beta, if beta is positive, that means that the velocity increases downstream, you have an accelerating flow. If beta is negative, the velocity decreases downstream, that means it is a decelerating flow. Okay. For a constant flat plate flow, the boundary layer thickness increases as x power half. For a stagnation point flow, it is a constant. If the angle is less than 90 degrees, the boundary layer thickness will decrease as you go downstream. If it is greater than 90 degrees, the boundary layer thickness will increase as you go downstream. And of course, in between you have the stagnation point flow, for which it is a constant. If beta is greater than 1/3, then the shear stress increases downstream, whereas if it is less than 1/3, the shear stress decreases downstream. So, this is the class of solutions for which you can get boundary layer solutions. Okay. And I went through this in some detail in order to show that the boundary layer equation has a very specific form for all of these. This form can be solved exactly only for the case where the potential flow corresponds to the flow in a corner. Okay. However, these solutions, the Faulkner-Scarn solutions for the boundary layer equations are important because they give us some intuition into the flow in other cases. Okay. They give us insight into the flow in other cases, and let us go through that in a little bit of detail. Okay. So, you get these numerical solutions for the Faulkner-Scarn equations. Okay. Similar to what we had done for the flow past a flat plate and the stagnation point flow, okay, I can plot, okay, eta is equal to y by delta of x, okay, on the x axis, that is I am in this particular case I have x and I have y. Okay. I could have a corner flow, but I still look at the distance from the y axis, okay, scale that by delta, okay, to get eta. Okay. And I know that u x is equal to u times df by d eta, okay, where u is in general a function of x. Capital U is the velocity of the outer potential flow in the limit as y goes to 0, okay, which means that the scaled velocity u x by u of x is equal to df by d eta. So, I can plot u x by capital U is equal to df by d eta. Okay. Far away, you have to attain the free stream velocity capital U, that is in the limit as eta goes to infinity, the velocity has to go back to the potential flow velocity. Eta goes to infinity while y star goes to 0 simultaneously. If u x is equal to capital U, that means the scaled velocity is just equal to 1. So, far away it has to reach 1. And we looked at various solutions here. Okay. All of them depend upon the value of df by of the value of the parameter beta that we had, which was equal to m minus 1. Okay. For the Blasius flat plate boundary layer, where m was equal to 1 and beta was equal to 0, we got this solution here, okay, which looks something like this. Note that the shear stress is proportional to d square f by d eta square. Okay, that means that you have to numerically calculate the value of d square f by d eta square as in order to calculate what the shear stress is. Okay, so, this let us call it as m is equal to 1. I am sorry, beta is equal to m is equal to 1 and beta is equal to 0. This is the flat plate Blasius solution for the boundary layer. If you plot this for the stagnation point flow, you find that it goes something like this. It of course approaches 1, but it approaches it faster. The reason is that the boundary layer thickness is a constant, okay, and therefore, because the flow is accelerating downstream. So, this becomes for m is equal to 2 and beta is equal to 1, the stagnation point flow. Okay. And as you increase even further, you will get something like this. Okay. This is for m greater than 2. Okay. What happens if m becomes less than 1? Okay. That corresponds to something that does not have a constant velocity far away. If you recall, m less than 1 corresponds to a flow that looks something like this. Okay. M less than 1 or beta less than 0. Okay. If I took a solution for m is equal to qualitatively, if I take for beta is equal to minus 0.05, I will get something like this. Okay. It approaches 1 much slower. Okay. I have exaggerated that here, but it approaches 1 much slower. Okay. At a value of m is equal to minus 0.0904, okay, at a value of beta is equal to minus 0.0904. Okay. Something important happens. Okay. At the value of beta is equal to minus 0.0904, the solution is such that the slope at the origin, okay, the slope at the origin note that this is df by d eta. Okay. The slope of this will be the second derivative. The slope at the origin is equal to 0. Okay. Slope at the origin is equal to 0. The slope is proportional to the shear stress, because the shear stress is equal to dux by dy, which is 1 over delta times dux by d eta. Okay. So, that shear stress is equal to 0 at the surface. The slope is equal to 0. Okay. So, what this implies is that as I if I expand it out, if I expand out the phenomenon here, okay, if I just look closely at the origin alone, okay, if I just look closely at the origin alone, okay, for m is equal to 2 I get a slope like this, m is equal to 1 I get a slope like this, m is equal to 0.05 the slope comes here. At m is equal to minus 0.0904 the slope itself is 0 at the origin for the numerical solution. Okay, for m is equal to minus 0.0904 the slope itself is equal to 0. Okay, this is I should write this as eta versus f df by d eta. Okay. So, the slope is decreasing as beta decreases. Okay. It comes down to 0. Once it comes down to 0, if you decrease beta any further beyond minus 0.0904, the only solution is that the velocity has to go negative. Okay. Once the slope goes to 0, if you decrease it further, the velocity has to go negative. What does a negative velocity mean? Note that positive velocity, that means that you have flow in the streamwise direction along the plate. Negative velocity implies that there is flow that is going opposite to the main flow within a small region. Okay, there is flow that is going opposite to the main flow within a small region. Okay. So, let us plot that. Okay, let us plot the velocity, okay, in this. So, this was the velocity for m is equal to 1 or beta is equal to 0. Okay. At beta is equal to minus 0.0904, the slope is equal to 0 at the origin. Okay. At that value, the slope is equal to 0 at the origin. You can see that the slope is equal to 0 at the origin. Okay. If you decrease beta below that, what has to happen is that the velocity profile has to look something like this. That means there is a region close to the surface where the velocity is actually opposite to the mean flow. Okay. And then you have the second point at which you have 0 velocity. Okay. So, that is what the numerical solution for the velocity field for these Fock-Nernst-Cahn solutions tells you. Beta is equal to 1 is the Blasius flow past beta is equal to 0 is the Blasius flow past a boundary a flat plate. Okay. In our Fock-Nernst-Cahn solutions, pi by 2 correspond to beta is equal to 1. Okay. As you opened up the corner, you ultimately reached a flat surface for which beta was equal to 0, corresponds to m is equal to 1, 180 degrees. If beta going below 0 corresponds to the angle going below 180 degrees. Okay. So, betas, okay, so if you recall, this was beta is equal to 1, beta is equal to 0 was just this one. Okay. And beta becoming less than 0 would basically correspond to a flow that goes something like this, m less than 1 or beta less than 0. Okay. So, for beta less than 0, you find that there is a velocity profile which has a backward circulation, okay, very close to the surface. So, beta less than 0, when beta reaches minus 0.0904, the shear stress becomes 0. As it decreases below that, you have a region where there is a backward circulation very close to the surface. So, what that means is that there is a separation of the boundary layer from the surface. There is 2 points at which the velocity is equal to 0. Okay, at the surface itself, there is an intermediate point within the flow at which the velocity is equal to 0, and in between the velocity is going backwards. Okay. That is when you have a boundary layer in which the velocity is decelerating. Note that for a flat plate, the velocity is a constant. For the stagnation point flow, the velocity is accelerating downstream. For the flat plate, it is a constant. When you make the angle greater than 180 degrees, the velocity actually decreases because beta is negative. U goes as x power beta, which goes as a negative power of the downstream distance. So, this is a decelerating velocity profile. So, these are specific solutions for the boundary layer equations for the particular case where the velocity had a power law dependence upon the x coordinate. How can this be used to understand flow past a general object? Okay. So, let us look at the simplest case. Okay. I will take in this particular case the flow past a cylinder. Okay. Simplest is to consider a 2-dimensional cylinder. My potential flow solution predicts a symmetric velocity profile, which we had obtained using complex variables previously. The potential flow is predicting something like this, okay, a velocity profile that is symmetric about this plane of symmetry. Okay. What about boundary layer theory? Okay. I can calculate the boundary layer thickness locally based upon the local mean velocity and whether it is locally accelerating or decelerating. Okay. As I showed you, the mean velocity here corresponds to effectively a stagnation point flow. Okay. A stagnation point flow for which beta is equal to 1 or m is equal to 2, for which the velocity increases proportional to x as you go downstream. In this particular case, this is the x coordinate. Okay. This is the x coordinate and this cross stream direction is y. So long as the boundary layer thickness is small compared to the radius of curvature, this corresponds to a stagnation point flow. Okay. So, this the velocity increases proportional to x. As I go downstream, that acceleration decreases. Of course, at the upstream edge, it has to accelerate to go around the object. As I go around, the acceleration decreases until I come to this point, where this basically corresponds to the flow past a flat plate. Okay, because the flow is tangential to the surface and the velocity is nearly a constant. So, this corresponds to a flow past a flat plate. For that, you have a boundary layer which is increasing proportional to x power half. In this case, the boundary layer is a constant. So, this basically corresponds to beta is equal to 1, this corresponds to beta is equal to 0, the flat plate. If I go a little bit downstream, of the top and bottom of the cylinder, I will come to a flow which basically looks like this one. Okay. There will come a region at which beta is equal to minus 0.0904. Okay. There will come a region that is slightly ahead of the upper and lower surfaces, at which beta becomes negative. Okay. At the upstream edge stagnation point, it is 1, at the top and bottom it is 0. If you go a little bit downstream, it will become negative, and once it becomes negative, the shear stress is going to go to 0 and you are going to have. Okay, so, here you have a velocity profile which is basically a Blasius boundary layer profile. Okay. If you go a little bit downstream, okay, once beta becomes minus 0.0904, the shear stress at the surface goes to 0. Okay. And if you go a little further, you will have a region where there is a recirculation at the back, okay, where the boundary layer has come off the surface. There is a region where the flow is in the opposite direction, very close to the surface, and then there is another point at which the velocity is equal to 0. Okay. So, there are 2 points at which velocity is equal to 0, one is at the surface itself and the other is a little distance away in the decelerating portion behind the sphere. Okay. And if I plot the locus of all points at which the velocity is equal to 0, okay, I will get something that goes like this. Okay. And within this region, because the flow is going opposite to the mean flow, I am going to get a velocity profile that goes something like this. Okay. I am going to get a velocity that goes something like this, okay, which is recirculating in this region. So, at this point where the shear stress is equal to 0, that is where you see the start of a recirculating region behind the sphere. Okay. And because this boundary layer comes off the surface, there is another location at which the velocity is equal to 0. Okay. And within the region, okay, within the region that is traced out by these two, okay, where the velocity is equal to 0, you have the flow that is going in the opposite direction. This region is what is called the wake, okay, where the flow is going in the opposite direction. The reason is because behind the sphere you have a decelerating potential flow velocity. In a decelerating potential flow velocity, if the value of beta goes below this value of minus 0.0904, there is a recirculation at the back and the boundary layer separates from the surface. You have another surface on which the mean velocity is equal to 0, which goes all the way into the fluid. And between these two regions, you have a wake region where there is a recirculation of the flow is going in the opposite direction. That is why the potential flow solutions are not applicable for these kinds of bodies where you do have a separation in the decelerating flow. Okay. The boundary layer solution is telling us that when you have deceleration in the outer velocity, the boundary layer separates from the surface, potential flow solution is no longer valid there. There is a wake region where the velocity is, there is a recirculation of the velocity, and the velocity close to the surface is opposite to the direction of the mean flow. And the reason that you have a non-zero drag on these surfaces is that the pressure in the wake is actually very small. Okay, the pressure in the wake is much smaller than the potential flow pressure upstream. If the flow were potential flow, both upstream and downstream, the pressures would have been equal. But because there is a wake where the velocity, where there is a recirculating region, pressure in that region is much smaller, and because of that you have a drag force. It is called the form drag. This boundary layer separation always occurs in what are called bluff bodies. Okay. Bodies which have a non-zero cross section ahead of the flow. Okay. If you want to prevent boundary layer separation, you have to use what are called slender bodies. Okay. Aircraft wing, for example, are slender bodies. They are optimized in such a way that there is no boundary layer separation, or there is boundary layer separation very far downstream. Okay, very far downstream. Okay. The flow around it, okay, there is no, okay, the flow around it is such that there is no deceleration anywhere along the flow, or deceleration is sufficiently small that beta never reaches this value. Okay. And if beta never reaches this value, you will never have a separation of the boundary layer. The shear stress on the surface will always be non-zero, okay, and you will not have separation of the boundary layer. Mm-hmm. So, this is the additional piece of this. This is why boundary layer theory is important. Even though potential flow predicted that there is a solution everywhere, boundary layer theory tells us that at certain locations, if the velocity is decelerating, the boundary layer is going to separate from the surface, and your potential flow equations are no longer valid in that separated region behind in the wake. Okay. In that wake, you have to use you have to analyze it separately, because the potential flow solution is no longer valid, and because the pressure is very small in the wake, basically the drag force that you get is due to the pressure exerted by the potential flow on the upstream side. Okay. So, this completes our discussion of boundary layer theory. We managed to get solutions for a very specific case, for a particular case which corresponded to potential flows, which are flows in a corner. Only for this particular case we were able to get analytical solutions for the boundary layer equations, but the intuition that we developed is more general. Thickness of the boundary layer, its dependence on the kinematic viscosity and the mean velocity profile, and what it tells us about boundary layers attachment to surfaces and their separation in a decelerating flow. These are all far more general concepts which are important because they tell us about the limitations of potential flow. Okay. So, this completes our discussion of boundary layer theory. And we will, in the next class, we will look at some additional features of flows in which there is vorticity. So, we will briefly discuss vorticity dynamics before we go on to looking at turbulent flows. So, we will see you in the next lecture.